Section 1.3, linear functions. So we're just kind of continuing our review here of functions. Linear functions we should all be fairly familiar with. So I'll move pretty quickly through this section since it's review. So a function is a linear function if it comes in this form. So this is what we call the slope-intercept form. We call it that because in this expression, f of x equals mx plus b, m represents the slope, and b, this is the y-coordinate of the y-intercept. So we'll have a y-intercept of, to write it as an ordered pair, 0, b. All right, and the x-coordinate of the y-intercept is always 0 because that's what puts it on the y-axis. And our method for graphing a function when it's given in this form is we usually find b on the y-axis. So right here we say b is kind of the initial or starting value of the function that occurs on the y-axis. And then m is the rate of change or the slope of the function. All right, so remember m, this is rise over run. Okay, another way that we can express this using what we call the slope formula, it's the difference of the y-coordinates, like if we're given 2 points, y2 minus y1 over x2 minus x1. So just kind of jogging your memory on some of the formulas and concepts relating to linear functions. And the domain and range of any linear function, as long as it's non-vertical and non-horizontal, they'll both be all real numbers, so negative infinity to positive infinity. So increasing and decreasing functions, the slope is what determines whether the function is increasing or decreasing. Or in some cases we have a constant function, and a constant function is just a horizontal line if we were to graph it. But here are the rules. F of x equals mx plus b is an increasing function if m is greater than 0. Okay, so if the slope is a positive number, and what that graph will look like, over here I'll just do a little sketch, is it will look something like this. Okay, so as we look at this graph, as we sort of read it from left to right, that's the way that we read graphs. If we see that the y values are increasing, right, looking at each of these ordered pairs as we go from left to right, if the y-coordinates are getting larger, that's what we call an increasing function. Okay, and then a linear function is decreasing if m is less than 0. So what that looks like is as we look at this graph and we're looking at those y values, as we go from left to right, they'll be getting smaller. Okay, so that's what a decreasing function looks like, or a decreasing linear function. And it's constant if m is equal to 0. That's what just gives us a horizontal line. So for this first example of this section, we want to determine whether a function is increasing, decreasing, or constant, meaning a horizontal line. And here's the information we're given about this function f of x. It's a linear function and it goes through these two ordered pairs, 2, 3, and 0, 4. We want to find its slope and we want to say whether it's increasing, decreasing, or of course, if it's a constant function. So here's what we'll do. We're going to use the slope formula, which I mentioned before. So slope, this is going to be that m value. And the formula for finding the slope, if you have two ordered pairs, is the difference of the y's, so y2 minus y1 divided by the difference of the x's, x2 minus x1. So although this is a really kind of simple formula, it's pretty easy to mess up. So let me show you how to avoid messing it up. We have these two ordered pairs up here. So I'll call this point, this first one, 2, 3. Let's call this point number 1. And I'm going to label these two ordered pair, or these two coordinates. I'll call this x1 y1. Okay, so point number 1, that gives us the x coordinate x1 and the y coordinate y1. And this other point, 0, 4, I'm going to call this point 2. And we'll label those x2, y2. All right, I'm going through this trouble because if you make a mistake and mess up the order of, either these, this difference up top or this difference in the bottom, you'll get a sign error, meaning you might get a positive where you're supposed to have a negative or vice versa. So here we go. I'm going to carefully plug these values in here. So in the numerator, y2 minus y1, so that's going to be 4, that's my y2, minus my y1, which is 3. And then in the denominator, x2, which is 0, minus my x1, which is 2. Okay, and then I'll just simplify this. I get 1 over negative 2. So negative 1/2 is my slope. So I'll put a box around that because that is the first thing that I wanted to find. And by the way, you could have labeled this point P1 and this point P2, and it would have worked out fine. But you just have to be consistent with how you label the x and y coordinates of each of those points. So we got this slope m equal to negative 1/2, and the important detail here, since we're trying to determine whether it's increasing or decreasing, this is a negative number. This is less than 0. So that means that we have a decreasing function. So I'll say since m is less than 0, f of x is decreasing. All right, pretty straightforward, and we can definitely check our answer really quickly, just sort of giving ourselves a visual confirmation. If we just plot these 2 points, they're pretty easy to find. The first one is 0, 4, so that's actually our y-intercept. So 0, 4, that's up there. And then we also have 2, 3. So that ordered pair 2, 3 is right here. And pulling out my ruler, I can sketch in this curve, or sketch in this line. And it looks something like that. My picture isn't perfect, of course, but close enough. And we can observe that it is decreasing, right? As we read this graph from left to right, we see that the y values are getting smaller. And just another way that we could observe the slope. Remember, it's rise over run. So there's my rise, there's my run. We can visually see that using this rise over run interpretation, we can see that the rise, it goes down 1, so negative 1, and the run, it goes to the right by 2. So there's our slope of negative 1/2, just another way of sort of interpreting that number. But that's all we needed for example 1. Let's keep going. So interpreting slope as a rate of change. This is really what we care about in this class. We are going into calculus here, and calculus, as we'll see, is all about rates of change. So let's see how we can deal with and benefit from linear functions with this interpretation. The population of a small town increased from 1,442 to 1,868 people, I presume, between 2009 and 2012. Find the change in population per year if we assume that the change was constant between those years, 2009 and 2012. So the change being constant, this right here tells us that we have a linear function. All right, because it turns out that the rate of change is just the slope of this linear function. Okay, and if the slope is constant, that means that the slope is just some real number. Like in this last example, the slope was -1/2. So constant change, that indicates that we're talking about a linear function. So how do we come up with a rate of change? Well, it turns out the rate of change is just the slope of this linear function. So rate of change is just equal to the slope. So we want to find m. Now this is a little trickier than the last example because we aren't just given a couple of ordered pairs, x and y's. We're given some information about population change. But it turns out that sort of coded within this word problem here, we just have two ordered pairs. The ordered pairs in this case aren't going to be x and y. They're going to be in this form. The input value is going to be t, and the output value is going to be population, which will depend on time, depend on the year. So I'll call it p of t. So we have to be deliberate about how we define t and our population. Let's talk about t for a second. We could just have t be, the year or years since the year 0. But I think that we can define t in such a way that the numbers aren't so big, because if we did that, then I'd be plugging 2009 and 2012 into my slope formula, and those are just bigger numbers than I feel like dealing with. So check it out. Here's what I'm going to do. Now we want to know, what is our t value going to be right here. So we know that the year that's associated with this population is 2012. So how many years since 2009 is 2012? So you might be able to just come up with it and say, 3 years. But really what we did to find that t value is really just the difference between 2012 and 2009. Okay, so like initial minus final. And we just get 3 from that. So that's why up here we have 3 as our t-value. Okay, so now we're getting close to doing our slope. And the way that we need to do that is carefully plug in these values into the slope formula. So rather than using x and y here, I'm going to use t and p of t. So we can call this our t1, and we can call 3 our t2. All right, and then this 1,442, normally I would call this y1, but here I'm just going to call it p of t1. All right, and then the 1868, this is going to be p of t2. All right, I promise that we're doing the same slope formula here. Really, I'm just including the context that it's not just x's and y's. We're talking about time values and population values at those times. So what our slope formula is going to be, normally, I'm going to erase this in a second, but normally it would be y2 minus y1 over x2 minus x1. But given the context of this problem, what it's actually going to be is it will be the difference of the p's. So p of t2 minus p of t1. And then in the denominator, it's going to be t2 minus t1. Okay, so same formula, just with the added context of us dealing with a function that actually represents something meaningful. But when it comes to plugging it in, it works the same way as a normal slope formula. So we'll have p of t2, which is 1868, minus p of t1, which is 1442. And the difference of the t values, that'll be 3 minus 0. That's t2 minus t1. Again, be careful about order. And I take this difference and I get in the numerator 426. In the denominator, I get 3. Important note, just the units here. In the numerator, these population values were number of people, right? So 426 people. And in the denominator, this was years. Because I'm about to do the final calculation here, just doing this division, and I get 142. And this is applied calculus. We deal with all different kinds of units here. You know, 142 what? What are we talking about here? This is a rate of change, kind of like I was alluding to in the previous section. When we have a fraction like this, where the numerator and denominator have units which are distinct from each other, we're usually looking at a rate. And the rate in this case is going to be people per year. With the per coming from the division sign. Okay, kind of like miles over hours is miles per hour. So I'm going to put a box around this because remember what we were asked for in this problem was find the rate of change in population, or the way they phrase it is change in population per year, right? This is the thing that indicates that we're looking for a rate of change. And there it is. So each year between 2009 and 2012, there's this constant rate of change of 142 people per year. So since this is a positive number, I'll give you a second to think about it. Is the population increasing, decreasing, or is it constant? Well, positive rate of change indicates we're increasing. So the population increases by 142 each year between 2009 and 2012. All right, so example 2 here, it's really just another slope formula problem, but with this added context of, we're looking at an application where we have population changing over time. But the big takeaway from this is that slope and rate of change are the same thing when we're looking at applications such as this. All right, and then here I just boxed up the slope formula for you, but we've already talked about this plenty, so I'll move on to the next example here. Example 3 looks like a business application. A clothing business finds there is a linear relationship between the number of shirts N that it can sell and the price P that it can charge per shirt. In particular, historical data shows that 1,000 shirts can be sold at a price of $30, while 3,000 shirts can be sold at a price of $22. And we want to find and interpret the rate of change. Okay, so this last sentence, find and interpret the rate of change. We want to find a slope. Okay, rate of change, wherever we see rate of change, we should be thinking slope. Okay, but we're going to have to read through this again and make sure we understand what our variables are and what the units are. Okay, extra close attention to the units. So we have these two variables, N and P. And N is the number of shirts that it can sell, and P is the price that it can charge per shirt. And we're given some information here. 1,000 shirts can be sold at a price of $30, and we can assume this is 30 per shirt. And 3,000 shirts can be sold at a price of $22. So this is really looking like a couple of ordered pairs here, right? We have a N value and a P value, and then another N value and another associated P value. So, first of all, our ordered pairs are going to look like this. We have N as we're going to think of this as our independent variable, and P is going to be our dependent variable. Okay, and I'm setting it up this way because when we read through the problem, we're trying to figure out which variable depends on which is affected by the other. And the way that this is phrased, I'm kind of looking at this sentence right here. The number of shirts N it can sell, and the price P that I can charge per shirt. And looking at how we are given these values, 1,000 shirts can be sold at a price of $30. So it's like 1,000 shirts, that number determines the price that we can charge. Okay, so let's come up with a couple ordered pairs here. So we should have two ordered pairs. What's the first one? And we should be looking at that second to last sentence here. So 1,000 shirts can be sold at a price of 30. So what's this coordinate going to look like? Well, 1,000 is the N value. And the associated P value is 30. And then we have one more ordered pair, 3,000 and 20. Right? Producing a higher number of shirts yields, it should be 22. Yields a lower price. All right. Oh, and this P, really, I should express it as a function of N. I could think of this as like P of N. Because now I want to label these, like always. I'll call this N1, and then 30 can be P of N1. And I'll call 3,000 N2, and this is P of N2. So now we can find the rate of change. The rate of change is going to be the slope, and the formula for this will be P of N2 minus P of N1 over N2 minus N1. Now I'll carefully plug in the values that I have. It was 22 minus 30 divided by 3,000 minus 1,000. Okay, and I can simplify this a little bit, taking that difference. I get -8 in the numerator, and I get 2,000 in the denominator. I can simplify a little bit more. We have a common factor of 8. I can write this as -1 over 250. So that is our that's our slope. In order for it to be a rate of change of something other than just, a line, the output values of a linear function, we need to think about what the units are. So the numerator, and you can look back to your formula here. This is usually pretty helpful at determining what the units are. The numerator, these were the P values, so the price per shirt. Okay, so I'm just going to add in some units here. The numerator was in price per shirt, or I'll say dollars per shirt. And in the denominator, we were taking the difference of these N values, and that was the number of shirts. So now we have to interpret this number -1 over 250. So what does this really mean? What does this tell us? Whoops. So first of all, it's a negative number, so something is decreasing, and the units are the price per shirt, the dollars per shirt, and the number of shirts. So what I'm getting from this is like thinking rise over run. If we go up by 250 shirts, so like if we produce 250 additional shirts, then what's going to happen to the price per shirt? It's going to go down by 1. So -1 is like our numerator here. So a way that I can interpret this is, how about I'll write it out like this in plain English. You save $1 per shirt for every additional 250 shirts that you buy. Okay, you could have spelled this out differently than I just did, but this is just, I wanted to give an answer sort of in plain English to indicate that I really understand what is going on in this problem. Okay, you also could have said, the price per shirt decreases by $1 for every additional 250 shirts you buy. There are a lot of different ways you could say this, but just to indicate that we understand what the rate of change actually is, we'll want to include a sentence like this. Okay, but again, just the hardest part about this is keeping track of the units, and figuring out what your ordered pair actually is, making sure you have the order correct, and making sure you plug into the slope formula correctly. Okay, but if you really strip it all down, it's just another application of this slope formula. All right, that's it for example 3. Example 6, example 4 on page 6. What we're doing here is we're talking about writing and interpreting an equation for a linear function. So moving past just slope and rate of change, let's talk about actual equations of functions. So f of x is a linear function with f of 2 is equal to negative 11 and f of 4 is equal to negative 25. Find an equation for the function in slope-intercept form, and then we want to graph f. So this is just another way that we could be given two ordered pairs, because when we're talking about a function, always draw one of my little Dr. Seuss machine diagrams here. Remember, x values go in, maybe I'll call this x1, and y values come out, y1, which we could also interpret as f of x1. So the output values, negative 11 and negative 25, are just like our y coordinates. So here are the two ordered pairs that I get from the information in this problem. I put 2 into f and out comes negative 11. So that's like my x1 and my f of x1. I put 4 into the function and out comes negative 25. So another ordered pair. Okay, so I'll call this x1 and f of x1. This is x2 and f of x2. So we want to find the equation of this line, but the first thing is always find the slope. We always want to get the slope first. And this is just going to be the difference of the y's over the difference of the x's. So we'll do negative 25 minus negative 11. Notice my parentheses because I have minus a negative. I don't want to get mixed up on that. Divided by 4 minus 2. So in the numerator, I am getting negative 14. In the denominator, I'm getting 2. So it looks like my slope is negative 7. All right, so that's good. Now that I have my slope, I want to come up with the equation. Remember, f of x equals mx plus b. That is our slope-intercept form. So the only thing that we're missing from this is that y coordinate of the y-intercept b. So there are a few different ways that we can find this, but what we're going to do is find b. One of the simplest ways to do it is to just look at this slope-intercept form, f of x equals mx plus b, and use some of the information that we have. So we know that our m is equal to negative 7, and one of the points on the line, I might just use 2, negative 11. It actually doesn't matter which point you use, you just need one point on the line. What I can do is I can use these values, and I can plug in to my slope-intercept form. I can put in negative 11 for f of x. I could put in negative 7 for m. And I could put in, for x, that x coordinate 2, and plus b. And now what I have is an equation with one unknown, so I can just solve for that b value. So let me simplify. Negative 11 is equal to negative 14 plus b. Add 14 to both sides, I'm getting that 3 is equal to b. All right, so now I have these two things. I got my slope is negative 7. I have b is equal to 3. So check it out. Here's my linear function. F of x is equal to negative 7x plus 3. All right, so find the slope. And then you can use the slope-intercept form, the slope that you found, and one ordered pair to solve for that y-intercept b. And we also want to graph this, so here's what I'll do. My y-intercept, I know, is going to be 3. So I'll just plot that point. That's the ordered pair 0, 3. And how about I use the slope now? So I know that the slope is -7, meaning that my rise over run, if I go over 1 unit, I should go down 7. So that would get me to that point right there. And 2 points are enough to define a line. So at this point, I'm just going to pull out my ruler and carefully draw in this very steep decreasing line. Okay. And I can even kind of confirm using these ordered pairs, because I know that like 2, -11 should be on this line. So if I find that ordered pair, you know, go over 2 and then go down 11, that brings me to this point right here. Or maybe I'll mark it in a different color. Right there, that's the point 2, -11, which should be on the line, and sure enough it is. Okay, so I'm a big fan of having all these little tricks that you can do to sort of visually confirm that you did the problem correctly. Okay, so my graph does go through that point. That gives me a little bit of confidence that I did this correctly. All students who get those really high test scores are in the habit of doing little things like that to verify that their work is correct. So I would strongly encourage developing those little tools and tricks for checking. But yeah, we're good on that one. Let's look at example 5, another business application here, manufacturing problem. A toy car manufacturer's total cost consists of a fixed overhead cost of $3,200 per month. So that's an important number. And when I think of fixed overhead costs, I think of just flat rates that this business is paying every month to stay operational. So this is like paying for energy, keeping the lights on, paying employees' salaries, things like that. Okay, continuing on, plus production costs of $40 per unit. So this is like a variable cost, which is going to depend on the level of production. So this might include like, cost of materials for making these toy cars. What we want to do is express the total cost as a function of the number of units produced. Okay, so this is saying like our dependent variable is going to be the number of units produced. And then we want to draw a graph of the function. If the manufacturer can sell each toy for $168, how many do they sell each month? Or how many do they have to sell each month to break even? All right, so I say we sort of take one thing at a time here. The first thing we're asked to do is express the total cost as a function of the number of units produced and draw the graph of the function. I think once we have that, it'll be easier to move on to this second part here. So let's try and do that. Let's try and come up with the total monthly cost. So a good place to start would be defining our variables. So remember, it says that we want to express this function as a function of the number of units produced. So how about we define a variable? Let's let x equal the number of units produced. Okay, and since all these values, or the overhead cost was given per month, we could say per month. Okay, and we could also define the function itself because we're trying to come up with a cost function. So let's also let c of x be equal to the monthly cost. Of producing x units. Now we should be able to come up with this function pretty quickly because suppose that we don't sell or we don't produce any units. Like, what is going to be the cost if x is equal to 0? Well, we're always going to have that overhead cost of $3,200. So we can, we know we're going to have this ordered pair 0, 3,200. That's our y-intercept already. Okay, so we know that this is going to be plus 3,200 on the end of our function. Right? What ordered pair will we have, if we produce one unit? Well, it's going to be that 3,200 just plus another $40 to pay for that one unit that we produced, right? So that'll be 3,240. Okay, if we sold 2 units, there would be another $40. So that's why for our first term of our function, it's going to be 40x. Okay, that $40 per unit ends up being the rate of change of cost relative to, the number of units that we produce. Okay, so this is it. This is our function. We didn't really have to solve for the slope or anything. We were just given that rate of change, $40 per unit. We were given that fixed cost of 3,200, and bam, there's our function. Okay, so now that we have that, let's start talking about this last question here. If the manufacturer can sell each toy for $168, how many do they have to sell each month to break even? So if they can sell each toy for $168, that's like our revenue, right? The amount of money that we can bring in by selling toys. So what this gives us is our revenue function, R of x. Okay, and this function is definitely going to involve that 168. Right, and that 168, that is the price per unit. So we'll just multiply that by the number of units, x. And there's nothing else to this function. That's all there is. There's just the price that we're selling them for and the number of those units that we sell. So here is our revenue function. Now, this question about breaking even. So when you break even, it means that your costs are equal to your revenue, okay? So break even, I'll just make a note of that. That means that your costs are equal to your revenue, so C of x is equal to R of x. Right, it just means that dollars out is equal to dollars in. Okay, so if we want to find the number of units, like how many units we have to sell to break even, we just want to set these two functions equal to each other and solve. Okay, so we want to set C of x equal to R of x and solve for x. So let's do it. C of x is 40x plus 3,200. R of x is 168x. And this is a fairly straightforward linear equation. Maybe I'll subtract 40 from both sides. Just trying to get x by itself. So then I'll have 128x equal to 3,200. Divide both sides of the equation by 128, and I get 25 is equal to x. So now let's answer this last question. How many units do we have to sell each month to break even? I'll say we must sell 25. And units, what are we talking about? Toy cars. Each month to break even. Okay, really important to be able to articulate clearly in English what is going on, acknowledging all the units and just, giving a very clear answer to the question. So now the last thing we want to do is we want to graph the function that we came up with. So c of x, let's graph c of x here to the right. And what we're going to do is be careful about how we set our scale on our x and y axes. Okay, so the x-axis is going to be down here. I might just label this so x, and that's the number of units. And the y-axis, I'm actually going to call this my c-axis, or it's going to be in dollars, so I'll just say dollars up here. So I want to graph this. It's a linear function. I have a y-intercept. We already made a note of that. We have the y-intercept is 0, 3,200. Our slope is going to be 40, so we can use those two pieces of information to graph this pretty quickly. But 3,200, that's a very large number. And notice that I only have so many, tick marks on my dollar axis here. So I want to be kind of careful about how I set my scale. So I have to be able to make it to at least 3,200 and actually higher because this is a positive slope. So here's how I think I'm going to set my scale. Let's have this be 1,000. So 4 little tick marks up is 1,000. This will be 2,000, 3,000. So essentially what I'm doing is each little square represents $250. Okay, so 3,000, there's 4,000, and up at the top 5,000. I think that should give us enough headroom here to graph this. Okay, so let's find our y-intercept, or our dollar intercept. At 3,200, that'll be right around here. Just put that point there. So finding the slope, now I have to define, how am I going to set up my x-axis? So the only x value that we really have seen in this problem is this 25, right? 25 toy cars has to be produced in order to break even. So I know I have to make it at least that high. I would like to see that ordered pair on this graph. It might make sense to do a little table of values though. So over here, off to the side, I could have input values x and output values c of x, which I could obtain by just plugging into my cost function, right? So I know if I put in 0, I get 3,200. Let's put in 25. If I put in 25, I get out 4,200. Okay, so 4,200 is the cost of operating if I produce 25 toy cars in a month. So let's just make sure that we can get to 25 on our x-axis, at least. Maybe have that kind of centered in the graph. So what do we think that we should count by here? I have 20 to work with, 20 little boxes here, from here to here. That's 20. So if I count by 2s, I think that would be pretty reasonable, because then I would make it up to 40 over here. And that would put 25 somewhere kind of in the middle. So let's do that. Let's count by 2. So that'll be 2, 4, 6, 8. There's 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 2, 4, 6, 8, and then we're up to 40. So let's place that ordered pair, which is at 25 as the x coordinate, and 4,200 is the y coordinate, so that's going to be right about here. And I'll label it. That is 25, 4,200. Okay, and we know that this is a linear function, so I can just draw a line through those 2 points because 2 points define a line. So there we go. There's the graph of C. All right. I also am interested in seeing what the revenue function is going to look like when we graph it. Mostly because it's going to be really easy to graph because R of X, like I could very quickly make a little table of values. X, R of X. I have the ordered pair 0, 0, right? Just plugging into this function, 168 times 0 is going to be 0. And I also have the point 25, 4200. And I know that I have this ordered pair because remember, when X is equal to 25, C of X is equal to R of X. All right, but you also could just plug 25 into R of X and you would get the same number. So here's what the graph is going to look like. I'll graph it using a different color. So we have these 2 points, the point at the origin 0, 0 and 25, 4200. So let me sketch this in. So there is our revenue function, R, graphed in the X $ coordinate plane. And what you might be noticing is that these two curves intersect at X equals 25, at that point of break even. Okay? And this is good to see because if we look to the left of X equals 25, what we see is the purple line is below the blue line, meaning that our costs exceed our revenue, which is not good. That's not really where we want to be if we're running a business. The whole point is to make money. If we look to the right of X equals 25, so over here, we see that the purple line is above the blue line, meaning that the revenue, the money that we're bringing in, exceeds the amount that we're spending to run the business. This is good. This means that we are in profit. So this graph is very, very important. And sort of seeing this line in these two regions. Over here to the right, we are in profit. Okay, so we are in the black over here. Okay, so one of the first assignments that you're going to do in this class is a discussion which revolves around break-even analyses. Okay, that's what we did here, where you'll have to find a cost function, come up with a revenue function, be able to find this critical X value, this input value, at which we break even. So this example 5 in this section is a very, very important one, a good one to study from, and a good one to guide you through that discussion. Moving along here. So I've already said this a couple times. 2 points determine a unique line. So 2 points of interest in this section will be the intercepts of the line. Okay, so as long as we have a linear function whose graph is not vertical and not horizontal, we're guaranteed to have a y-intercept and an x-intercept. And those can be very valuable to know. Okay, so the x-intercept of a line is a point where it crosses the x-axis, and the y-coordinate is always 0. So it's always going to be in this form C0, where C is some real number. And a y-intercept, same thing, but other way around. It intersects the y-axis, so the x-coordinate is 0. So if we want to find an x-coordinate, or an x-intercept or a y-intercept, we just want to set the y-coordinate equal to 0 to find the x-intercept, set the x equal to 0, and we can solve for the y-intercept. So let me show you what I'm talking about in example 6. We want to find the intercepts of this linear function, 2x minus 5y equals negative 15. This is the graph. This does have a graph which is a line. I know it's not in that form y equals mx plus b. It's not always going to be given in that form. So here we're going to work with this sort of standard form of this line. Let's find the x-intercept. So to find the x-intercept, we want to set y equal to 0 and solve for x. So here we go. 2x minus 5 times 0 is equal to negative 15. So that's plugging in 0 for y. So I just get 2x is equal to negative 15. So divide both sides by 2. X is equal to negative 15 over 2. Which I could rewrite as just 7.5 if I wanted to, negative 7.5. And I'm writing it that way because I'm going to find this on the graph in a second. Decimal form is a little easier to locate when we're looking along a real number line. Okay, so I'm going to write this as an ordered pair because this is an x-intercept, so it's going to be negative 7.50. Okay, I would be totally okay with you giving this answer as negative 15 over 2, 0. Doesn't matter to me. Your online homework shouldn't care either. Okay, for the y-intercept now, we're going to, yes, set x equal to 0 and solve for y. So I'll do that. 2 times 0 minus 5 times y is equal to negative 15. So I just have negative 5y is equal to negative 15. Divide both sides by 5. I get y equals 3. So I have a y-intercept at 0, 3, right? X coordinate is 0, y coordinate is 3. And I can plot these 2 points off to the right. So my y-intercept, which we just found, was at 0, 3, so I'll just put that point right there. Our x-intercept was at negative 7.5 on the x-axis, so counting back, 2, 4, 6, 7.5. There it is. And two points determine a unique line, so I'll just draw in a line through those 2 points. And there it is. There is the graph of our linear function. And one way that you can check your work, I am an obsessive work checker, which is a really good, a good way to be in a math class. What I can do is I can take my equation, which was 2x minus 5y equals negative 15, and I can just solve for y in this equation to get it into slope-intercept form. So I would subtract 2 from both sides, or subtract 2x from both sides. Divide both sides by negative 5, so I would get 2/5 x plus 3. And the reason I do this is now I can sort of verify, like, okay, my y-intercept is at 3, check, I got that on my graph. The slope is 2/5, so what that means is if I go up 2, I should go over 5. And this is just kind of a visual check, like, okay, up 1, 2, and then I should go over 1, 2, 3, 4, 5 and land on that point right there, which I did. So that looks good. Just kind of checking my work in any way that I can. I'm feeling confident about that answer. And that is the last problem on this section reviewing linear functions. So I zipped through certain parts of that pretty quickly because a lot of this should be review. If you're rusty on some of this, that's okay. This is your chance to practice it. If you have questions or concerns, reach out to me. I'm happy to work with you in office hours, help you with the homework questions and all that. Otherwise, I'll see you in the next section. 1.5 on quadratic functions. Benji says hi.